Linear radiofrequency accelerator. The idea of accelerating positive ions with the help of an alternating radiofrequency field was suggested by Ising in 1925. The first working accelerator was constructed by Wydrow in 1928. A schematic diagram of a typical linear RF accelerator is given in figure. Ions to be accelerated are injected into a series of metallic electrodes in the form of coaxial cylindrical hollow tubes. One terminal of a high voltage RF accelerator is connected to the odd numbered electrode cylinders and the other terminal is connected to the even numbered cylinders. The ions essentially travel along the common axis of the tubes. Suppose the ions reach the gap between the nth and n plus 1th cylinders at the instant which the nth cylinder is positive and the n plus 1th cylinder is negative, and the RF is at the relative maximum value of that half cycle. The ions will then receive an acceleration towards the later cylinder and thereby gain an energy QVM, Vm being the maximum amplitude of the RF voltage. The ions then enter the cylinder with a velocity say Vn plus 1. Once inside the electrode, they move into a field-free region and consequently their velocity and energy remains constant. Since the ions move with constant velocity inside a given cylinder, they drift in it. The cylinders are also referred to as drift tubes. If Ln plus 1 is the length of the n plus 1th drift tube, the time taken by the ions to travel the length of this cylinder will be T is equal to Ln plus 1 by Vn plus 1. The length of the tubes also adjusted that this time of the traverse within the electrode is independent of the length of the tubes. The period of RF is also adjusted to be equal twice this time of traverse. That is, Ln plus 1 by Vn plus 1 is equal to 2 by 2. Under these conditions, the ions will reach the next gap between the cylinders at the time when the phase of the RF has changed by 180 degree. The electric field in the gap will again be accelerating one for the positive ions. They will receive another increment in their energy by the same amount as before. Thus, if n is the total number of accelerating gaps, the total energy of ions after coming out the accelerator is nqvm. As a result, we can increase the maximum energy of the ions by increasing the number of cylinders without increasing the value of RF voltage to unmanageably large magnitudes. Now the energy of the ions can be written as 1 by 2 mvn square is equal to E0 plus nqvm. E0 being the initial energy with which the ions enter the accelerating tubes. For proper acceleration at each stage, Ln by Vn is equal to 2 by 2 and Ln is equal to lambda by 2c into root of E0 plus NaVm, where lambda is the wavelength of the RF. Before World War II, the frequency of the RF waves available was limited and therefore the wavelengths were larger and the length of the electrodes were unmanageably large. However, after the war, high power, high frequency RF source become available and the length become reasonable. The LINAC is more useful for electrons because their velocities reach near c very rapidly and thereafter their velocities are reasonably constant and thus the cylinder's length also become constant. Cyclic accelerators. One disadvantage of the linear accelerator is the unveiled overall length. In an effort to overcome this difficulty, Lorentz convinced the idea of constraining the ions to move in spiral orbits with the help of magnetic field perpendicular to the motion of the ions. The length of the orbits will then automatically increase with the energy of the ions to remain in tune with the increasing RF field. The device was named Cyclotron. The first machine was built in 1932 by Lawrence and Livingston. They used a dipole magnet with a pole piece diameter of 11 inch and RF oscillator of only 2 kV potential. Cyclotron. It consists of two flat semicircular boxes in the shape of the letter D and hence called Ds. Surrounded by a closed evacuated vessel, the Ds are parallel in between the pole piece of a dipole magnet. An RF potential of 10 to 20 MHz frequency is applied between the Ds. A source S positively charged ion of mass m provided a beam of ions with a suitable initial velocity v in the plane of the Ds. The presence of the magnetic field B forces this ion to move along a circular trajectory of radius r is given by the Lorentz force equation BQV is equal to mv square by r. When the ion passes through the space between the dies in one direction, suppose that the RF potential of the Ds are such that the Ds towards which the ions are moving is at negative maximum with respect to the other. The ions will be accelerated and thus gain in energy by an amount QVM inside the D. The ions move through a region free of electrical field since field does not exist inside hollow conductor. Consequently, their velocity remains a constant until they reach the gap between the Ds at a point almost diametrically opposite to the one they just crossed. However, since their energy is now more than, they will traverse a semicircular trajectory whose radius is more than the previous orbit. As seen from the above equation, at the next gap, the ions receive an additional energy increment if the phase of the RF field is adjusted so that the instant the ions reach the next gap, the RF voltage advanced by exactly 180 degree in phase. The process is repeated. The time taken by the ions to travel the semicircular trajectory inside a D can be written as T is equal to pi r by nu. The increase in velocity of the ions is compensated by the increase in path length inside the D, and therefore the time traversed inside the D is a constant. The condition to be satisfied for the ions to receive acceleration at the gaps is that within the time travel T, the RF field exactly reverses its priority. In other words, T should be just equal to the half of the RF field. T is equal to tau by 2. This gives the following result called the cyclotron condition for the angular frequency of the RF. Omega is equal to QB by M. These are the top view and side view of the schematic diagram of cyclotrons.